Good morning, everyone. Today we have a notable speaker, Dr. Carriquiry. She was appointed as a Hagler Fellow at the Hagler Institute for Advanced Study at Texas A&M University, and we are very happy to have her here. Dr. Carriquiry is a distinguished professor and the holder of the President's Chair in Statistics, as well as the director of the Center for Statistics and Applications in Forensic Science at Iowa State University. The center was established in 2015 as a way to apply more objective science in the forensic field when dealing with human evidence. She received a master's degree in animal science from the University of Illinois and the master's degree and PhD in statistics and animal genetics from the Iowa State University. She researches applications of statistics in human nutrition, bioinformatics, forensic sciences, and traffic safety, and has published over 100 peer-reviewed articles in corresponding academic journals. Welcome, Dr. Kirk.
Thank you. So thank you, everybody. Do you guys hear me, or do I have to? Yeah? Okay, great. So this is not going to be a highly technical talk. I just want to introduce you to the subject. And CSAVE is the center that Valeria mentioned. Go check this website. We have lots of data, lots of things, everything publicly available that you can play with if you're interested. So let's see, does this work? No. Okay.
Sorry.
There we go. Okay, so this is a little, now I went all the way. Oh, okay. Okay, there we go. So this is a little bit of an outline for the talk. I know that I'm not gonna get to handwriting, but I put the slides there just in case. So I'll tell you a little bit about the motivation, why this type of work is important. Then I'll tell you about the forensic question that we try to answer. I'll go into some statistics, otherwise this would not be an interesting talk. And then I'll tell you what happens when you have really, really strange data to work with, the kind of things you have to do. And so let's see if this works. Yes. This gentleman here is called Keith Harward. And Keith Harward, in his early 20s, he was a sailor, and he was stationed in Norfolk News in Virginia in some big carrier. And at the time he was there was this horrific crime that was committed. Somebody wearing a sailor's uniform went into a house, murdered the husband, sexually assaulted the wife. And in the process of doing that, the person bit the wife multiple times. And so, very long story short, there were all these ups and downs. At the end of the day, the police focused on Keith Harward for some very unrelated issues. And he found himself in court, and he found himself accused of the murder and the sexual assault. He spent 36 years in jail until the Innocence Project, using DNA analysis, finally was able to prove that he was innocent, that he could not have possibly committed that crime. And so he was released, I think 6 or 7 years ago, something along those lines. He is now in his 60s. All right, so the science that was used to put Keith Harward away is what's called forensic bite mark. Now, forensic bite mark is very, very, okay, this is what we might call junk science. There's absolutely no scientific or empirical justification for the use of this evidence. So what happens is, if somebody bites you, the forensic odontologist will go and get, they will get a cast of the teeth of the defendant, and then they will match the cast to the injury, and they'll say, to the exclusion of all other teeth in the universe, these were the teeth that made this mark. And these guys are dentists, and they sound very, very scientific. And so juries, which are composed of not our peers, really, people that couldn't get out of jury duty, do not really understand and, are very impressed. So bear with me, this is a little bit of a busy figure, but a few years ago, several years ago, a couple of these forensic odontologists started wondering, there were so many wrongfully convicted people that had been released, that had been put away on the basis of forensic bite mark testimony, that these two guys said, are we doing things right? Or are we, is this correct what we're doing? And so what they did is they went back and they got about 80 old cases, between 80 and 90 old cases, and where there were injuries, some abrasion type injuries that had been introduced into evidence. And they got about 45 of their colleagues to participate in this test. So what they did is they showed each one of the 45 people, they showed all 80 images and said, what do you think? Is this a human bite mark? It's probably a human bite mark, or is it an animal bite mark? So these three options. And so those are the, oh, sorry, and there was another option, or I have no clue. So 4 options. And so those are the 4 colors that you see in this plot. Each one of the rows on the plot represents one of those 80 or 90 samples. I can remember how many. And of course, you would hope that everybody would have the same opinion, right? So that when it was a human bite mark, everybody would say human bite mark, and so on and so forth. But you can see, and we don't know what ground truth is here, but that was not the purpose. The purpose was just to see what kind of agreement of reproducibility there would be in this type of assessment. And you can see that there is no reproducibility whatsoever. So with a few exceptions, like the very top 2 or 3, and a couple others, the very bottom 1 or so, the responses are all over the place, right? So people simply do not agree on, they cannot even agree on whether this is a bite from a dog or from a human, let alone identify the exact set of teeth that made this injury. So so this is really what we would call junk, and this is probably one of the worst in forensics. By the way, it's still being admitted in court because the U.S. System is such that once it's admitted once, there is precedence. And so, if it's, so, judges that come later will say, well, dude, it was admitted, so why should I not admit it? And so typically these things perpetuate. The one state where this is no longer admissible happens to be Texas. And Texas, believe it or not, has an extraordinarily progressive Forensic Science Commission, the Texas Forensic Science Commission. And they've done deep dives into all kinds of forensic technologies, and in particular, bite marks. And they said, you cannot do this in Texas courts. This is no longer admitted, which is fabulous. So in 2009, there was this really important report by the National Research Council. And what they did is there was a panel assembled, and they took a real deep dive into all of forensic disciplines. And what they came up with was that, with the exception of forensic DNA analysis, everything else was on very shaky grounds. And so very little science, and the worst culprits, or the disciplines that were in worse shape, were what's called the pattern comparison disciplines. And pattern comparison disciplines are things you have heard about a million times, right? Latent print analysis of fingerprints and ballistics. Can you tell from looking at a bullet or a cartridge case whether this particular gun may have fired that bullet? Shoe and tire tread. So if you find a shoe print at the crime scene, can you say whether the defendant's shoe made that print? Bloodstain patterns. If you kill somebody and there's a wall behind, you'll see a stain, blood stain, and people claim to be able to tell the manner of the injury. Was Was the person shot? Was the person stabbed? Was the person hit with a baseball bat? And so on. Handwriting, question documents, forgeries, and so on, and good old bite marks. And so CSAFE, by the way, was created a little bit as a consequence of this report. And our mission is to look at pattern comparison disciplines and digital evidence. Okay, let's see. So what is the forensic question that there's a million different forensic questions, but I'm going to focus on one. So suppose that you have a crime and you go to the crime scene, and at the crime scene, you may find different types of evidence. In this particular crime scene, what you see are bloody footprints or shoe prints. And what you want to know is, and there's a spent cartridge case over there, so somebody got shot. And there might be different types of evidence, biological evidence. That's like the winning the lottery, because of course you can do forensic DNA analysis and some other type of analysis, digital evidence, physical evidence like glass fragments of fibers, so this kind of stuff, or patterns like fingerprints and shoe prints and bullets and so on. And so the question, there's a million questions that can be asked. I am going to ignore all of them except the question of source. And the question of source is simply, was the defendant or the suspect the source of the evidence at the crime scene? So you want to place the defendant at the crime scene. And how do we do this? Well, typically you have, let's say, a bullet that you recover from the crime scene, and then the defendant still has his or her gun. And so you take that gun, you shoot the gun a few times, you get some reference shots, and then you compare the crime scene item to the reference items to see whether you can say something about how similar they might be. And so these are examples, and at the very top there, I'm showing you 2 cartridge cases, and this is what's called the breech face impression. This is the bottom of the cartridge case. And then there's, of course, some prints over there, some fingerprints. And what I'm going to talk about today, I'm going to mostly use an example from firearms examination. So questions? If you have questions, stop me, yeah? So what is the status quo for pattern comparison evidence? Well, there's no measurements. Nobody measures anything. The examiners typically just compare the 2 items side by side visually. And the conclusions are subjective. So if you were a fingerprint examiner, you might start, so this on the right might be the latent print from the crime scene. You mark what they call minutia, and then you see whether the same minutia appear on the reference print. And then you go, yep, there's enough minutia here to for me to say this finger was the one that left this print. And I'm telling you, I've been doing this for 40 years. I have lots of experience. So I have absolutely no doubts that this is the finger. And so that's pretty much the way it works in all of these disciplines. So here's another illustration, firearms. So you can see, so those are bullets at the bottom there. And I'll show you a picture of a bullet later, but examiners compare the striations, those little marks that, and that line in the middle there is because what they do is they use this comparison microscope that allows them to place the 2 samples side by side, and then they can rotate one or the other until, the little scratches actually coincide, and that's what she's doing up there. And so this is what the AFTI, AFTI stands for the Association of Firearms and Toolmark Examiners. This is their professional grouping, let's say. And this is what they say. So the comparison enables opinions of common origin to be made when the unique surface contours of 2 tool marks are in sufficient agreement. So what does sufficient agreement mean? Agreement is significant when the agreement in individual characteristics, in other words, the scratches, exceeds the best agreement demonstrated between tool marks, blah, blah, blah. If this sounds incredibly circular to you, then you're right. It is completely circular. In other words, agreement is sufficient when you think it is. And so what has happened is that there's been all kinds of studies to see how reproducible this type of conclusions are, and they're not very reproducible or even repeatable. So if you show a firearms examiner the same set of samples, let's say 6 months later, oftentimes, and I go about between 35 and 40% of the time, they tend to reach a different conclusion. So that's not so good. And then they go and testify, and the testimony is very, very strong. For example, no other gun could have fired this round. You know, that's pretty strong. To a high degree of ballistic certainty, whatever that may be, but it sounds important. And so that also is, and you know, or to the exclusion of all other guns in the country. These are the type of testimony some of these guys offer. And you know, there is absolutely no there's no scientific justification for any of those statements. There are no well-designed studies to understand whether they, what the accuracy of these examinations is. It is well known, for example, I mean, it has been shown that anytime an examiner says, so, and this is inconclusive, in reality, ground truth says it should have been an exclusion. So, and when I say there's a bias to against excluding, I'm talking about something like in this type of, in the black box studies are called, where they look at these things, you know, every time you look at an exclusion, 95% of the times, it should have been an elimination. Sorry, an inconclusive, 95% of the time should have been an elimination. So it's really very iffy. All right, so where's the statistics in all of this? So now let's get a little bit more formal. Where do you start, right? So if you're a statistician and you have to sort of develop some formal approach to analyze this type of data, the first thing you need to do is kind of set up the problem in a way where you can do something with it. And so the first, I think, to formalize the source problem was Dennis Lindley in the dark ages, 1977. So none of you guys were alive at the time. And even I was only like 20 years old at the time. So imagine. If you haven't read this paper, you should. It's very short and it's a little jewel of a paper. So I strongly recommend you read this. So Lindley says, all right, so we need to decide whether this is these two items have a common source or they have a different source. Let's think of it in terms of a hypothesis test. And so we have two competing hypotheses. HP stands for the prosecution's hypothesis, and then HD stands for the defense's hypothesis. And the prosecution hypothesis, of course, is this guy, the defendant, is the guy that shot this. It's his gun. And the defense's hypothesis is somebody else, not my client, somebody else. And so how do you go about even thinking about this, right? So, and Lindley was working on glass fragments when he came up with this thing. So there were measurements. And so Lindley says, well, you know, so we have measurements, X1 all the way to XM from, let's say, the crime scene evidence. And then we have measurements from the item we get from the suspect. And let's assume for simplicity that the means X bar and Y bar are normally distributed with means theta 1 and theta 2. And for now, the same variance. So sigma square is the same. And so the the prosecution's hypothesis is that theta 1 is equal to theta 2, right? So all measurements have a common origin. And the defense's hypothesis is that these two sets of measurements come from different populations. And so when would you, I mean, this is intuitive, right? When do you fail to reject the null hypothesis? Well, I mean, what do we normally do when we carry out a t-test or what have you? We measure the distance between x bar and y bar, right? If that distance is small in standard deviation units, right? We fail to reject, right? The null hypothesis. And so, yep, this would be evidence in favor of same source. But there's another thing, right? The match has to be rare. So if all of these values are like around theta 1 and theta 2 in the middle of those distributions, then you're going to find lots of this is not going to be telling you much. But if these values are rare, so if we're talking about values in the tails, for example, and you find a match, then you may be onto something. And so how do we account for this rarity? Lindley says, and if you know Lindley, no surprise here, well, we have to be Bayesians. And so what he did is he put a prior on theta 1, theta 2. He said, these are exchangeable. They come from some prior with mean mu and between between samples, variance tau square. And now, hold on. Oh, there we go. And now we could look at, we can say, all right, let's look at the odds. So what are the odds of observing a small difference, what we have observed between x bar and y bar under the same source hypothesis, the prosecution's hypothesis, over the over the chances of observing the same evidence, but now under the defendant's hypothesis, the defense's hypothesis. So if you go to that paper, this is before MCMC, this is before computers, this is before all kinds of things. And so it's absolutely spectacular to look at the derivation. This is all analytical derivations that Lindley did. And so he said, all right, let's look at the numerator. And remember, in the numerator, we have a common theta, right? Because they both come from the same distribution. And the measurements can be assumed to be independent, at least conditional on the theta. And so you get that the numerator is just the integral of the two marginals, conditional marginals, times you average over the prior values for theta. In the denominator, of course, you are assuming that theta 1 and theta 2 are different. And so you have the product of those two integrals. And I didn't put the entire thing here, but if you follow this derivation, and solve analytically, you end up with an expression that depends on two terms. There's other stuff, but the two terms that are important are these ones. X bar minus y bar squared, that tells you something about the closeness, how similar these two sets of measurements are. And then z minus mu squared, that tells you about the rarity, how far away from this common mean these measurements are. And z here is it's a function of the two sample means. It's like a weighted average. And so this ratio that we're going to be calling a likelihood ratio, that likelihood ratio is a one number summary that tells you about the similarity and also the significance of that similarity, how rare these things are. And so it so happens that if you remember Bayes' rule, and this is what's called the odds form of Bayes' rule, you start from some prior beliefs, the prior odds ratio, which is to the very right over there. And then you gather evidence, right? So this is before any evidence is gathered. Then you gather evidence, and then you update your beliefs, right? So given the evidence that's presented in court, you are the juror, And so you update your beliefs and come up with what's the posterior odds, which is what are the odds that in fact the prosecution is right and this defendant is the source of the evidence at the crime scene. And so what are those? I'll say very little about this, but what are those prior odds? Well, in our system, the prior odds should be very low, right? Because our system says innocent until proven guilty. So you need to give the defendant the benefit of the doubt. In some cases, you have some information, or at least you need to be non-informative, let's say that. So if there's, 21 persons in an island, and one person appears dead next morning, right? There's 20 possibilities, would you say? And so any one person is 1/20 likely, right? In the non-informative case, if you know nothing else, to be the murderer. So in any event, this typically is a small value. And so the evidence has to be pretty overwhelming in favor of same source for you to end up with a posterior odds that's high enough for you to convict, right? So I'll talk about the likelihood ratio in the rest of my talk. And I'll talk about what do we do when, so we know how to compute a likelihood ratio. So if I give you a bunch of glass fragments and I'm telling you we're measuring the refractive index in each one of these glass fragments, then you can assume that refractive index is normally distributed or has a t distribution or whatever the distribution might be. And then you can compute those, you can actually come up with a numerical value, but for the likelihood ratio. But what do you do when the data are weird? So for example, images. And so here's some examples. And so this is just a handwritten document. And that's a crime scene shoe print. The next might be the reference print that I get from the suspect. The one at the very back over there, I don't know how many of you guys are familiar with bullets. All right, so bullets is if you have ammunition, right? The ammunition there's a cartridge case, that's the bottom round thing. And then at the very tip is the bullet, and that's made of lead. And when you shoot a gun, there's an explosion inside the cartridge case. And if it's a semi-automatic pistol, the cartridge case is ejected. And the bullet, because of this explosion, shoots down the barrel of the gun. And that's what I'm talking about. And the barrels of guns have what's called rifling. Hold on. All right, so this is a bullet, right? So that's the top and this is the bottom. And I'll show you now, most guns have what's called rifling. And so if you look at the bullet around the circumference, there tends to be 5 or 6 areas called lands. Land engraved areas. This is a land. And these are the striations that the examiners look at. And those striations are left because as the bullet travels down the barrel, there's all these microscopic imperfections in the barrel of the gun. And so it leaves these marks. All right, so the examiners will compare striations. They will say there's enough coincidence here. I'm going to call this a match or an identification. And as I said before, this is a completely subjective assessment. And so this is the inside of a barrel. So the barrel has these sort of ruts. Those are called grooves. And what those are like, they're not parallel to the length of the barrel. They're sort of like at an angle. And what those things are there for is they make the bullet rotate. And so the bullet comes out of the barrel rotating, and that makes the flight more stable, the flight of the bullet more stable. And so what we're looking at are the lands, which are the areas between the grooves. All right. So here's one approach, and here's one of the things we are doing at CSAFE. So the first thing is we have purchased this equipment called confocal microscopes. And confocal microscopes, maybe some of you guys have heard about those. They allow you to get a three-dimensional image of the topology, surface topology of the bullet. So if that's, let me see, if you see my, yeah? So can you see the, whoops, sorry. Can you see the bullet right there, right? And so this is what you see. This is the surface of one of those lands, right? It's one of those areas in the bullet. This is just a colored image that shows that at each XY coordinate, so now we can think of this as a surface, right? And so we have the XY coordinates, so this would be, dang it, I don't know how to do this. This would be the X coordinate, this would be the Y coordinate, right? And at each one of those, at very, very, very high resolution, this is like 0.6 of a micron. So this is very, very high resolution. We get a depth. So we end up with a flat file, which is XYZ. And so the question is, if we have those measurements, now we have measurements, right? So now we're golden. What are we going to do with those measurements? And so here is, I'll start from the top and move down the bottom. So here's an algorithm. Oh, here's how you create data for analysis out of this type of stuff. So the first thing we do is we say, all right, let's look at a cross section of the bullet of the land, and then let's look at the depths in that cross section. And so if you look at the bottom, you see that things break up. So this is not a good area. And as you move up, the striations also sort of break up, right? And so there's a good area there that is marked by that red, where the striations are pretty stable. So that means if I move a little bit up or if I move a little bit down, the striations are still the same. And so the way we identify that, the computer identifies that, is using a cross-correlation function. And so we sort of take measurements or use the measurements at the area where the cross-correlation function is least variable as we move up and down. So the next figure shows you a sideways view of that top over there. The two little mountains on the sides, those are the grooves. And so the area in the middle is the land. The third plot shows you a single pixel representation of that surface that we have over there. And again, you can see the grooves on the ends. And then what strikes you? If you look at the third plot down, the dominant feature there is the curvature, right? And if you look, and that's not a smooth surface because you see all these tiny little mountain thingies. Those are the features you're interested in. But that curvature dominates. And so the algorithm first cuts off the two groove areas. And then what we do is we fit a loss, a non-parametric regression function that's to that surface. That's a blue curve over there. And then we just remove the curve, the fitted curve from the observed curve and work with the residuals. So this is just the residuals of that non-parametric fit, that blue non-parametric fit. This is what we call the signature of a bullet land. Okay, and so the ups and downs over there show you just the surface, the topography of that bullet land once we remove the curvature. This is not essentially what we do is we take those two, imagine taking the two ends and kind of flattening the curve. It's not exactly right because there's a little angle, which, but it works pretty well. And so now I have this land, and then somebody said, this is from the crime scene, and then somebody gives me the bullet that we got from the suspect, And lo and behold, I overlay both signatures over here, and this is what I see. And so now you're really in good shape because now you can quantify the difference between these two signatures, right? And so we take about 7 different measurements. We look at the location of each peak, or the dislocation, if you will, the difference in the locations, the differences in the heights, the differences in the depths, the number of consecutive peaks, and the number of all kinds of different things. We end up with about 7 measurements. And then the question is, looking at those 7 measurements, can I say anything about whether these two bullets were fired from the same gun or not? And so what I'm showing you here is from some experimental data where we knew ground truth. So we had a bunch of bullets. We knew which ones were fired from the same gun and which was fired from different guns. And for all those pairs, we created all possible pairs. So we had a bunch of same gun pairs and a bunch of non-matching pairs, let's say. We computed the value of those features. So the first one is called consecutively matching stria. The next one is consecutive non-matching stria. I don't know, the number of peaks, the CCF, the cross correlation function, and so on. And you can see, the dark blue is known non-matches, and the light blue is what we observe for the known matches. And there seems to be something going on there, but none of these one alone will allow me to separate the pairs that were fired from the same gun and the pairs that were fired from different guns. So what we did in this particular case is we said, all right, can I combine these features into some sort of a similarity score? And there's a million ways to do this. And so what we chose to do is to fit a random forest. Let's say if we combine all these features using a random forest, what am I going to observe? It turns out, and you guys know what a random forest is, right? Most, okay. It turns out that what we end up with was highly discriminatory. So let me show you. So okay, I should have had another slide here that shows what we got in the data that we developed this with, but that's not, so, we did the right thing, right? Training set, independent testing said very, very, very low error rate, but that doesn't tell the whole story. The question is, if somebody were to give us another set of bullets, would we still be able to tell, correctly? And so here's 2 sets of bullets. One we got from the Phoenix Police. I'm showing you this too. One is from the Phoenix Police Department. The other one is from the Houston Forensic Science Center, which is one of the best crime labs in the country. And what they did is they didn't tell us ground truth. And so in the case of the PD, each one of these columns is a different gun. And for each of these different guns, they gave us 3 reference shots. They said, these 3 bullets were from barrel A9. These other bullets were from barrel C8, and so on and so forth. And then they gave us a bunch of unknowns. So 1, 2, I don't remember, 3, 4, 5, 6, 10 unknowns. And they said, can you guys associate these 10 unknowns with the barrels? And the trick here is that some of those unknowns may not have been fired from any other barrels. Some, maybe 2 were fired from the same barrel. So everything was possible. They didn't tell us. And so what you see here are the random forest scores. And so we compared unknown bullet N to the 3 test shots from barrel A8, the 3 test shots from the next barrel, the next. And orange here means very high similarity score, and gray means very low similarity score. So here's the scale. And so we said N matches the 3 test shots from barrel A8. And then B matched the 3 test shots from barrel C8 and nothing else. And then nothing matched the test shots from barrel U, the last. And bullets Q, Y, and Z didn't match any of the reference shots. And so that's what we submitted. And it turns out they were all right. So we didn't make any mistakes. Houston was trickier. What they did is they gave us same story, but in the case of Houston, for example, 2 of the unknowns, the second and the third here, were from the second barrel, and then nothing from this barrel, and again, 2 of the unknowns were from this barrel, and so on. Ignore this last part. So again, we made no mistakes. And so it turns out this thing works very, very, very well. And so we are now in the process of piloting this algorithm in a bunch of real crime labs. So Miami-Dade, Houston Forensics, Kentucky, and who knows, those are the ones that have agreed already. All right, so I give you a similarity score. Let's say it's 0.8. What does that tell you? Is it a match? Is it not a match? And so what you need to do is remember that likelihood ratio that we were talking about, that we interpreted as, you know, the evidence we have observed is likelihood ratio times more likely under this hypothesis than the other. So how do we construct a likelihood ratio here? Well, what we do is we construct what's called a score-based likelihood ratio. And so how do we do that? So let's suppose that you have a very large number of pairs of bullets that are representative, you know, many guns, many ammunition manufacturers and so on, and you compute the similarity score for lots of known matching pairs and for lots of known matching pairs. And let's suppose that this is what you get. So the gray here is the distribution of the scores, similarity scores you would observe under for the different gun pairs, so the non-matching pairs. And the orange here would be the distribution of similarity scores you obtain from the known matching pairs, right? And so now I am and you know, the random forest is kind of nice because it gives you this similarity scores that are between 0 and 1 that you can sort of very loosely interpret as some sort of an empirical probability of same gun, of same source. And so now let's suppose that I have a case and I measure the similarity between the 2 lengths and I get a 0.8. So how likely is to observe a score of 0.8 if the bullets are from different guns? It's very unlikely, right? So you can think of the height of this empirical density as kind of representing the likelihood of observing that particular value. Whereas that value of 0.8 would be extraordinarily likely under the same gun distribution. And so a score-based likelihood ratio might be, for example, the ratio of, you know, 2.9, which is more or less the value of this distribution at that particular score, divided by 0.001, which might be the value of this distribution at the same score. And you get something like 2,900. And so the way you would interpret this is, given those reference distributions, observing a score of 2,900, observing a score-based likelihood ratio of 2,900 means that it is about 2,900 times more likely to observe this degree of similarity if the bullets had been fired from the same gun. So you don't say identification, exclusion, inconclusive. You offer a probabilistic statement, and then the jury may do what the jury may do. And so the idea here would be that they would take this likelihood ratio, they would multiply that by the prior odds, remember? And that would give them some idea of what the posterior odds are. Okay, so this is a fun one. So here in Houston, as a matter of fact, we tested the algorithm against the examiners. So there were about 35 examiners that participated, and the algorithm was examiner number 36. And they looked at about 570 pairs. And, by and large, the examiners and the algorithm agreed on identifications and exclusions, a couple differences. But there were 34 or 40% inconclusive decisions among the examiners, whereas the algorithm had 0 inconclusives. It was either similar or not similar. So in that sense, it was kind of very interesting because that might be an interesting tool for examiners to use. So I'm not going to get to handwriting, but if you're interested, I'll be happy to talk to you about this. Let me get to, this is a completely different problem. And here we're actually fitting a real model. Oh, come on. Maybe I should give another talk. Hold on. Okay, so one of the things we try to do in CSAVE is be transparent and we go for reproducibility. So if you get onto our website, this bullet algorithm, for example, is posted. So we post everything, all the data, all the algorithms, all the presentation slides, absolutely everything. And so some parting thoughts, there's a ton of work to be done. We are just scratching the surface a little bit. So if you're interested in this area, please consider. I don't know if you know what happened to Keith Howard. So after he was released, he got himself a partner and they bought a camper and they've been running around the United States, happy as a clam. And so he had a happy ending, bless his soul. And so I think that's it. Check the website and talk to me if you think this is something you'd like to do. 5 minutes. Excellent. Question. That's a very good question. And so we still don't, I cannot tell you exactly, but I can tell you that there's some ammunition that is very hard. And so it's very different. You won't see very many markings on those. And there's some guns that are extraordinarily high quality. If you ever want to commit a crime, buy yourself a Glock. Those guns have a different type of rifling. They don't have these grooves. They have what's something called polygonal rifling. So every algorithm, including ours, goes belly up. And so there's a few groups assembling very large databases trying to understand the effect of gun, the effect of ammunition, and so on. Yeah.
So something that I've heard from my fiance, because people represent judges can be very flighty about algorithms they can't understand. And in particular, something like a random forest, it seems like that black box nature might be hard for a judge to accept. Have there been any issues like with the legal system kind of disputing the validity of these black box algorithms?
Well, that's kind of funny because if there is an area where that's full of black boxes, that would be forensics. So, APHIS searches and DNA-based searches. And I mean, there's a million algorithms out there, all of which are black boxes. But you're right. I mean, not only judges, the lawyers don't understand these things. And so, every time you talk to a lawyer, they'll say, oh God, I got into law because there was no math. And so they hate this. But so that's one reason. So, I show you the random forest. We could have done deep neural nets. We could have done, all kinds of, and maybe increase accuracy a little bit. But random forest, you can kind of explain. Because, if you can explain a decision tree, and that's more or less doable, then you can go and imagine a forest full of trees. And so more or less this flies, but not much. This is going to be a huge uphill battle, yeah. Okay, well,
So if you want to use your algorithm in other countries,
yes.
like, do you have to retrain, like, to like meaning that said all can use?
I would probably do that. I mean, so if the mix of guns is more or less the same, then you would not. But if it's very different, and so there's a million gun manufacturers in the world, unfortunately. And then there's the super good guns like Glocks and 6 Hours. And then there's midnight specials like some of the Chinese guns that are, I mean, if you want marks, those will leave all kinds of marks. And but so I imagine you will have to decide depending on how you would compare that population to the population that was used to train the algorithm. Yes.
Are there any areas of forensic science where you said, for instance, there was high agreement, ballistic setting between people and algorithm?
Yes.
On the cases at least where people make decisions.
Yes.
Are there areas where you're developing algorithms where the people generally suck? but clearly out there.
Well, I can tell you, forensic ornithologists suck. But we don't even bother developing an algorithm, so I would not be able to tell. But latent print examiners are pretty reasonable. So if you look at, I think what algorithms do better than humans is resolve those cases where it's not clear. So those inconclusives. And when we compared the algorithm to the small, very small set of examiners, there was, examiners had one false positive and a couple of false negatives, and the algorithm didn't. But, in the big scheme of things, those were very small error rates, unless you're the person for which the false positive was made. So there hasn't been enough testing. So the next thing we're going to do is, so I showed you bullets, but we have similar approaches for handwriting, for shoe prints. What in the world? This thing. Anyway, for shoe prints, for handwriting, for fingerprint examination, and for blood spatter. So stay tuned. Yeah. So all of this data, if you're interested in, playing with this data, dive in.
Thank you very much again.
Thank you, guys.